Hello, my name is Grisha Waxman. The paper title is Patchcraft Self-Supervised Training for Correlated Image Denoising. It's a joint work with my advisor, Professor Michael Elad. We propose self-supervised training method for image denoising. We assume that noise can have non-Gaussian distribution. Noise is independent on image but can exhibit short-range spatial and cross-channel correlations. These assumptions are very practical since given a sensor, capturing corrupted images is relatively straightforward, but obtaining ground truth or estimating noise model is difficult. In RGB space, real image noise is typically correlated. Our training scheme achieves outstanding denoising performance, surpassing the competitors by a large margin. Let us dive into the details. Our scheme uses short video sequences. These sequences can be captured using camera burst mode. We allow small to moderate camera and object movements between the frames. From each video sequence of M frames, we construct an input and target image. We split the middle frame into patches of size p by p. For each patch, we find the most similar patch when searching in the rest frames of the sequence. We built a patchcraft frame by replacing the patches of the middle frame with the found neighbors. We repeat this process for all p-square possible splits, obtaining p-square patchcraft frames. We use the middle frame as input to denoiser and randomly choose one of the obtained patchcraft frames to be the target image. We present a lemma stating that training with our self-supervised loss is equivalent to applying stochastic gradient descent with clean targets, when the target noise has a zero mean and statistically independent of clean image and input noise. However, in our scheme, the conditions of the lemma are not satisfied, as the target noise can depend on both clean image and input noise. To reduce correlation between the target noise and network input, we use the following method. We define by R a difference between the input and target images. SYR is an empirical covariance between Y and R. SYR is a scalar. For each image in dataset, we get one such scalar. For entire dataset, we can plot a histogram of SYR. This histogram serves as a tool for identifying and removing faulty images with high correlation from the dataset. Here is an example of SYR histogram. It has a long left tail. We omit part of the tail for clarity of presentation. We prove that if the conditions of the lemma were satisfied, then the histogram would be a Gaussian. The histogram is not Gaussian. It is not symmetric, and its mean is shifted in relation to the peak. Yellow bar indicates the peak, while the black bar indicates the mean. To improve the histogram, we remove from the dataset all images for which SYR is less than a threshold S-mean. The threshold S-mean is set such that the mean of the resulting histogram coincides with its peak. We evaluate our methods through extensive experiments with synthetic and real image noise. Our training scheme achieves outstanding denoising performance, surpassing recent state-of-the-art self-supervised methods by a large margin. Let's conclude. We presented a novel self-supervised framework for correlated image denoising. Our method uses short video sequences for training. It applies patch matching for building patch graph images and uses them as the target images. We exclude images with high correlation from the training set. Our training method achieves outstanding denoising performance compared with the recent state-of-the-art self-supervised methods.